3.3, we're going to start taking a look today at something that seems intuitively like things you've seen before, increasing and decreasing functions. You have a perception of what that means already. We talk about it in an algebra, pre-calc kind of context. We're going to define it a little bit more specifically from a calculus perspective. And then the other thing that's in our section today is called the first derivative test, which is actually involving increasing and decreasing functions. That's why you see this happening within the same section. So first, definitions of increasing and decreasing. These definitions are quite similar to what we see in like the college algebra course that I sometimes teach. An interval is increasing when it has the condition that if x1 is less than x2, then f of x1 is less than f of x2. And we'll draw a picture for that. In order for x1 to be less than x2, it just means that it's occurring first on the number line, right? And the value at x1, whatever it is correspondingly supposed to be smaller, so this is f of x1, than the value at x2. And so we have an increasing function. Intuitively, if you looked at this, you'd probably tell me it was increasing because we read graphs the way that English is written. We read from left to right. And so the graph is going uphill from left to right. So this shouldn't look like something drastically new, right? All right, decreasing is quite similar. We still have this notion that x1 is less than x2, right? We still have to have the order of the x values the same. So we'll put them in there in the same approximate locations. Here's x1, and here's x2. But instead, we want the y value corresponding to x1 to be bigger than the y value corresponding to x2. So I'll put it up here. So here's f of x1. And then somewhere over here is f of x2. And again, if read from left to right, well, let's try that again. If read from left to right, this one would be going downhill, so we call it decreasing. Okay? All right, so we have a connection between increasing and decreasing graphs in the derivative, and that's what this next theorem is about. It tells us that suppose we have a continuous function on an interval. So if it's continuous, we can actually then talk about derivatives. If the derivative is positive, then we can say that the graph is increasing. And if the derivative is negative, that's the second one, then we can say that the graph is decreasing. And if the derivative equals 0, so derivative equals 0 is what we've been doing in the past two sections. If the derivative equals 0, then it is a constant. And in many cases, it means that it's a max or a min. Now, the first derivative test will actually help us to decide, is it a max or a min? But at the very least, we can say there's a constant there. Okay, it's 0. So imagine what this means, and let's actually draw a graph of an increasing function. So if you have an increasing function, like that, and you were to draw a tangent line, so I'll draw a tangent line, we'll use orange in here like this. It should be clear that the slope of that tangent line is positive, right? I have a positive slope there. So if the slope of the tangent line is positive, then that means the graph is increasing. And I've got the same description, but flipped on the second one. So if I've got a negative slope of a tangent line, it's easier to draw the curve first. Sorry, we'll do that first. And then I have a tangent line. Then this point right here, right, this tangent line where I've drawn it, is a negative slope. And that negative slope of that tangent line corresponds to a decreasing graph. Okay? So the increasing or the decreasingness of the graph is actually telling us whether we have a positive or negative derivative, and vice versa. And then we have this weird one here at the bottom that says if it's actually equal to 0, but it says on x on an interval. So imagine that we actually have an interval where we have a slope that's 0. So we have, I'll draw another graph here. an interval from A to B. And everywhere on that interval, I've got a slope that's 0, a derivative that's 0. The only way that can happen is if the graph itself were a flat or a horizontal line, right? So that's what this is describing. Now, if this is not on an interval and it's at a specific point, that's what we were seeing happen in sections 1 and 2 of chapter 3. So let's actually pull all this together then with the first derivative test. The first derivative test tells us how we can decide if we have a local or relative max or local or relative min. This is what I started talking about this morning about your quiz, and I realized, oh, no, that's what we're talking about today. Okay, so we've got a continuous function on AB, and C is a critical number. So remember, critical number means that the derivative is equal to 0 or the derivative does not exist. Okay, that's what a critical number is. So if we have a critical number somewhere in the interval, then if the derivative is positive and then it changes to negative, all right, so this is saying it's positive and then it becomes negative, i.e. it changes from increasing, because a positive derivative means an increasing graph. So this is taking the language we used in the last theorem and merging it together. So the derivative changes from positive to negative, which means the graph changes from increasing to decreasing. And if you could imagine a graph that's increasing and then it's decreasing, what's happening here at the top is what we would call a maximum. It's a relative maximum because we don't know what's happening later on in the graph, but in this nearby area, it's the biggest value. We can describe the exact same thing but flipped upside down, right? Image with part B, or 2. So if it goes from a negative derivative to a positive derivative, negative to positive, on an interval, that means that the graph itself, a negative derivative means a decreasing graph. These correspond to one another. A positive derivative means an increasing graph. So it goes from decreasing to increasing. And visually speaking, if you see a decreasing to an increasing graph, it means you have a minimum. So increasing to decreasing, decreasing to increasing, positive derivative to negative derivative, negative derivative to positive derivative. But what this doesn't say is what happens if there is no change. And that's what's happening on 3. If the derivative, I think that should say derivative. Yes, that's a typo. I think it's right in your notes, is it? Yeah, it's just a typo on my screen. I need to get that fixed. Okay, if the derivative has the same sign, and notice it doesn't specify which. It's positive and it's positive, it's negative, it doesn't matter, but the signs are the same. So you can imagine that means that a positive derivative means it's increasing. So it's increasing and then it does something where then it's increasing again. Okay, well it's not a max or min then, right? Because it was increasing and then it was increasing. Or it was decreasing and then it was decreasing. And you might be asking yourself, well, why would that even be a point of discussion? Let me actually draw you a graph where this happens, and I'll even define for you exactly what it is so that you can see it. The graph of x cubed is a really good example. Tangent graphs are a really good example as well. But the graph of x cubed looks basically like this graph. Draw it better. Something of that nature. If drawn well, which is definitely not drawn super well, this point right here actually has a derivative of 0. And I can define that I can prove that from an algebraic standpoint. If I were to take this derivative, what's the derivative of x cubed? 3x squared. And where does 3x squared equal to 0? At 0. There is a location where its derivative is equal to 0. But you can see that the direction of the curve doesn't change on either side of that, right? It's increasing on the left and it's increasing on the right. So when that happens, then we say that there's simply no local extrema. So that is a distinct possibility. You can't just say, oh, look, critical point, derivative is equal to 0. I have a max or a min for sure. You don't always. You have to check the surrounding values and see what's happening. Is it increasing and increasing? And you're not going to have a relative extreme at that point. All right, so let's actually see one done. So you can see all of the pieces at play, because there are a lot of pieces to making this decision and how these interplay with one another. So this graph is not necessarily a graph that you're familiar with. That's kind of the point. If I gave you a parabola, you would be able to tell me immediately, it's got a max or a min, I know. You don't know for this one, which is why we're doing it. So we're going to, directions say, identify the open intervals where it is increasing or decreasing. And we're actually going to do a secondary step in here. It's not written in here, but some of ours will, and so we'll go ahead and make mention of it so this kind of pulls all of our theorems together. And we're going to also identify any max or mins. And I'm talking about local or relative ones here. Okay, we're not looking at endpoints and things like that. And in particular, you'll notice that these graphs typically are given to you with no interval. Do you see that? And if you check further on the notes that I've given you, they're not intervaled graphs. We're looking on the entire number line, which means it's much more difficult to identify any absolute maxes or mins. And in fact, they don't have to have them. Okay, so what do? It says identify the open intervals where it's increasing, decreasing. Well, what this says that we need to do is we need to find critical points. Okay, so critical points, as we specified it earlier on in this lesson, are places where the derivative is 0 or doesn't exist. And we're going to have both things happening on this graph. Okay? All right, so let's find derivatives. This might be a good one for us to start out by rewriting that this is x plus 4x to the negative 1. All right, derivative. What is the y prime for this guy?
X minus 4x to the negative 2.
Okay, this part's right, but it's a 1, yeah. So 1 minus 4x to the negative 2nd. Is that okay with everybody? All right, that's not in a very friendly form right now. Putting it back into the other form that it was might be helpful. So I'm going to put it back into the form like this. All good? Okay, so we're going to look for places where this is equal to 0 or does not exist. Now, we can find out where this does not exist pretty easily. Where does this does not exist? At 0, right? And in fact, that doesn't really give us a lot of new information. We knew that from the original graph. What's happening at 0 on this graph? There's an asymptote, right? The denominator doesn't equal 0 at the beginning of the function, right? We've got an asymptote there, absolutely. So that does not exist is not going to be super helpful. However, even if it's not a max or a min, it could still be a place where we change direction. Imagine the graph, I'll just sketch it really quickly, of 1 over x, and it looks like this. The graph is increasing on the left, and it's increasing on the right. But if you do 1 over x squared, it looks like this. It's increasing on the left, and it's decreasing on the right. So we can still change increasing and decreasing potentially at an asymptote, even though we don't have maxes and mins. So that's a possibility, okay? So going back to our particular problem then, we need to figure out where, so this does not exist at x equals 0. We need to figure out where it's equal to 0. So when you do rational functions in a pre-calc or a college algebra course, the way you find where this is equal to 0 is you have the numerator equal to 0. The way you find where it does not exist is you have the denominator equal to 0. The problem with this function, the way that it's currently written, is that it doesn't have a single numerator. It has a whole number piece, and then it has a fraction piece, right? So we need to merge these two pieces into a single fraction in order to decide where does the numerator of the whole thing equal 0. So that's what we're going to do. We're going to create, I'll move this to the side, this as a single fraction, and we can do that by simply multiplying it by x squared over x squared. So this will become x squared minus 4 as my numerator, and x squared is my denominator. Yes?
In this particular case, wouldn't it just be simpler to set the equation equal to 0 and move one side over?
I will show that, and there is a possibility of doing that. I want to show a couple things along the way, but we'll show it from that perspective too. Yes, you're correct on this particular one. It would work really nicely because there's no linear term. But if I had an x term, like an x squared and an x term coming out of doing this, it wouldn't be very nice to do it that way. Okay, so I'll come back to Josh's question and show another option for this particular one in a moment, but you're right. Okay, so we want the numerator to equal 0. That's how a fraction equals 0, is if its top is equal to 0. Now, we had actually seen this earlier. We saw it, I don't remember if it was in 3.1 or 3.2. You are welcome, if you would like, to move the 4 to this side and take the square root. You need to be a little bit careful when you do that. What happens when you take the square root? Plus or minus. So that's fine if you'd like to do that. In general, this is not going to just be an x squared and a constant term. It could definitely have a linear term as well. And if it did, we wouldn't just be able to shift the 4 and then do some square rooting, right? We'd actually have to factor. So I'm going to show this one with factoring just because it will model a more broad picture of others that you'll see. So factoring is always going to be a possibility at this point. I shouldn't say always a possibility, but it's going to be a generalization of what you can do as opposed to a very specific one where we move the 4 and we take the square root. Though that works here just fine. How will this factor? X plus 2x minus 2. And if we set each one equal to 0, we will get x equals positive and negative 2, just like we would if we square rooted it. Okay, let me actually show you the other thing that Josh was pointing out from when we did this. Another option on this one, again, not always on every one, but it works nicely on this one, is if you have this piece like this, equal to 0, you could move the negative 4 over x squared to the other side. And you could multiply by the denominator to eliminate the fraction. And then you get to the same point that we would have gotten to where you have x is plus or minus 2. Okay? So that is another option. It just doesn't always pan out. And this one, it works great. So there's 3 different things you could have done. They will all lead you to the same conclusion, provided that you've made appropriate steps along the way. 2 and negative 2 and 0. We've got three different potential places where we have, well, 3 different critical points, right? 3 different critical points, positive 2, negative 2, and 0. So here's what we're going to do. We're going to create a number line. I'm going to go ahead and delete this part on the right-hand side just to have some more space to work, okay? So we're going to create a number line, and our number line needs to go in order. I know that seems sort of like a silly thing to say. Of course it needs to go in order, but I just want to make sure we're all on the same page. Remember that? So it goes in order. So we have 3 critical points. The first one that will be on our value is what? Negative 2. What's the second one? 0, and then 2. Okay, number line. What we want to know is we want to know on the locations that are in between these, what's happening. Do I have a positive derivative, or do I have a negative derivative? Or do I have a constant? And I'm not going to have any constants, I'll just tell you that right now. It's going to be positives or negatives on these intervals. That's what's going to happen. We're asking about the derivative being positive or negative. Remember, a positive derivative means an increasing original graph. But it's a lot easier to see if a value is positive than if an interval is increasing. It's a lot easier to figure out if something's positive. So here's what we do. This is called a sign chart, is that we use values in between these endpoints. So you can pick anything you would like before negative 2. And you're going to get the same thing in terms of whether it's positive or negative. So everybody in this room could pick a different number. So we could have somebody pick negative 100, and somebody could pick negative 1,000, and somebody could pick negative 3, and somebody could pick negative 2.5. All of you could pick different things. And again, as long as you made the appropriate arithmetic processes through that, everybody will get the same sign. And it's the sign we care about. So let's pick jointly a number that is less than negative 2 together. Negative 3. Okay, so we're going to pick negative 3. We're going to pick values in each of the intervals, so let's pick them first. How about a value between negative 2 and 0? Negative 1. There's usually some that just make sense to pick between 0 and 2. 1. And after 2? 3. You guys are so not adventurous today, but that's okay. All right, so we want to know what the derivative is at these values. So I'm going to put a note in here, so when you look back at this later, you remember what we did. We're going to check the derivative at these values. So in a very real sense, and we don't necessarily have to write all these pieces down, but we will for this one at least, we're going to find, oh wait, our function was called y. Y prime of negative 3, and y prime of negative 1, and y prime of 1, and y prime of 3. That's what we're going to find. All 4 of these values, they correspond to the red values that I've written on my sign chart. And we can do that using our calculator in a table really friendly, okay? So I'm told that this thing is working now, so we're going to try the document camera again and see if I can get that to focus for you. All right, so grab your calculator, and I want you to put an equation in your calculator. Which equation do I want you to put in? The original function or the derivative? The derivative. Please put in the derivative. We will graph the original function with it in a moment so you can see how these things correspond as well, because they're not necessarily what you would have expected, but they will correspond. All right, that's pretty good. The light's not on. It's a little bit better, I think. Oh, not there. We'll go to the side. Okay, so in y equals, I'm going to put in the derivative that we found, which was, I'll just write it as 1 minus 4 over x squared. If you want to write it in the negative exponent form, that's fine too. It won't hurt anything. And remember, your table should still be set up. If it's not, you can go into table set. So you hit second and then the table set button like this. It should say ask on the independent and auto on the dependent. If it's set up like that, you can go into the table. So that's the second button and the graph button. And we can actually put in negative 3, negative 1, 1, and 3. And what we care about is the sign. So what sign do we get when we plug in negative 3? It is a positive. I know you can't see my screen, but when it pops back up, I'm just writing the positives and negatives on the f of x notations that I had at the bottom. How about at negative 1? It's a negative. Positive 1, another negative, and positive 3, a positive. Okay, so I'm going to take a look real quick with you at this graph. Since our values go from negative 3 to 3, I'm just going to make my window go from negative 5 to 5. So in my window, I'm going to take my x max and min to be negative 5 and 5 respectively. And then I'm going to hit zoom 0. Zoom 0, wherever it is. What it actually does is it takes whatever x values you picked and picks an automatically good value for y. Oh my goodness, it's terrible because we have that asymptote happening. Let me change my window again then. You don't want that happening on my y-min. Let's make it negative 10. That's a little bit better. Okay, so can you see, again, we're not thinking increasing, decreasing, we're thinking positive, negative. The graph is initially positive, right? And then the graph slopes underneath the x-axis, so it's now negative. You jump over the asymptote, it's still negative graphed, right? And then it pops back up to being positive. So my f prime graph, or my y prime graph, looks something like this. And again, this will be here for you later if you look back at a video. Does yours look like that? Okay, Ian, check with Josh because his does. So check your window. Make sure your window looks something like this. It might be a window issue, Dylan. Try negative 5 to 5, 1, negative 10 to about 1. I have a feeling I know what's wrong with yours. what I'd like for you to do before we leave the calculator screen and looking at this, is I'd like for you to hit y equals and put in the graph of the original function we started with. You don't really need to keep the derivative one in there. We've already looked at it. We know what it looks like. And putting them on the same graph is sometimes really confusing. So let's just do for the moment x plus 4 over x. And let's just do a standard window. I don't know if that's going to be good, but I don't have near as much to go on this one as I do the last one. So we're going to do zoom 6 as a standard window. Oh yeah, that's a good window actually. So thinking about increasing and decreasing now. Does the graph increase at the beginning? Yep. And then do you see the decrease? Yep. And then you see another decrease after you move over the asymptote. You see the decreasing part at the beginning, on the right-hand side, and then you see it increasing again. So the graph for y, and I'll draw it over here too, is one of those ones with slant asymptotes. Y'all remember slant asymptotes from an algebra course somewhere? You don't want to admit it, do you? You can tell. Okay. So this is the graphs that I've drawn in while we were off screen. So this was our derivative graph. So it's it's positive, negative, negative, positive, increasing, decreasing, decreasing, increasing. They correspond to one another in those locations. But I want to show you what happens in the sign chart. So all of this is well and good, but to be honest, you could have avoided doing all of this at the bottom if you think more constructively about your sign chart. So when you put the -3 into the table and you got a positive, I'm going to put a positive on my sign chart here. And then we do the same thing for the -1 and we got a negative. And we did it for +1 and we got a negative. And then we did it for +3 and we got a positive. Everybody good so far? So think about what positive means. Positive means that the original graph was increasing. So over here, it's going up. And negative means that the original graph was decreasing, like this. And again, I have decreasing, and then I have increasing. So the images are not meant to show you how steep something's doing it or what the graph really looks like. It's just answering the question about increasing and decreasing, and we can do that with a real quick sketch of what that looks like on that interval. So answering the questions of increasing and decreasing, let me shift this up. The graph is increasing from -infinity until where? Where does it stop increasing?
At -2.
At -2. I know we plugged in -1, but -1 we had a different value. It's the -2 location. And then when does it start increasing again?
2.
At 2. So we put a u for union between these, and then we do a 2 all the way to infinity. Where is the graph decreasing?
-2, 2.
Is it -2 to 2?
Yeah, it has break at 0.
It has a break at 0. We have to identify the break at 0 because at the asymptote, there's no derivative. Therefore, the derivative is not doing anything. It doesn't exist there. So we would identify that there is a break in that, and it would look like that. So -2 to 0, and then 0 to 2. This is interval notation. If you're rusty on your interval notation, come see me, talk to the Success Center. It's really important, and you're going to be using it extensively in the rest of at least this chapter. We could also look at this, and we can identify, we won't go all the way down the bunny trail on this, but can you see from that sign chart where you expect there's to be maxes and mins? Where does it look like there's a maximum value?
At -2.
At -2. It's increasing, and then it's decreasing. This one's going to be a max. And it's going to have a min, likewise, over here, right? This one's going to be a min. So we could actually take the value -2 and put it back into the original function and find the corresponding y value, right? We could actually take the value +2 and we can identify our maxes and our mins from that information. Now, this question didn't ask us to do those pieces, but that's just another small piece that can change in the directions, and they will be asked on some of the other ones we do. Okay, everybody good so far? We'll pick up with several more examples next time.